Inside the reactor that grows the crystal layers of an LED or a power chip, every wafer must sit at the same temperature to within a single degree, or the film grown on it comes out uneven and the chip fails. A silicon carbide susceptor is the platform that makes that possible. The disc that holds the wafers absorbs the heating power and spreads it into a temperature field flat enough to grow a perfect layer across every pocket at once. The surface that touches the wafers is high-purity silicon carbide, better than 6/9 pure, so it releases none of the metal impurities that would poison a semiconductor crystal. That cleanliness is the first requirement. A susceptor that sheds contamination ruins the very layer it is there to grow. Silicon carbide holds its chemistry and its shape past 1600 degrees, far above the point where bare graphite would oxidize away, and it stands up to the aggressive hydrogen, ammonia, and chlorine-bearing gases of the process. The reactor can run hot and corrosive, and the susceptor stays intact. Its thermal conductivity runs high, on the order of 300 watts per meter Kelvin. So heat floods through the disc and evens out before it reaches the wafers, and its thermal expansion sits close to that of the wafers it carries, so the two heat and cool together without stressing the crystal. Here is the part that makes the name. A susceptor is a body that takes up energy from a heat source, it suscepts it. In these reactors, a radio frequency coil or a resistive heater drives energy into the conductive silicon carbide, and the disc itself becomes the hot element, then radiates that heat evenly up into the wafers resting in its pockets. The wafer is not heated directly, it is warmed by the glowing susceptor beneath it. The whole design serves one number. Because the conductive body spreads heat so well and its shape is tuned to offset the cooler edges, the temperature across each wafer face holds to about 1 degree. That single-degree uniformity is what keeps the epitaxial layer growing to the same thickness everywhere, deviation held under 1% across the wafer. Surface finish finishes the job. Polished to a roughness of 0.2 of a micron or better, the pockets hold the wafers flat, keep the gas flowing smoothly instead of tumbling, and give particles almost nothing to cling to. So the clean, even heat is not spoiled by turbulence or dust at the very last step. A susceptor is built around the wafers it must carry. Some hold a single large wafer, others, like the disc here, ring several pockets around a center one for a planetary reactor that spins each wafer for evenness. Pocket diameters follow the standard wafer sizes, from 2 inches up through 6, 8, and 12, and the overall disc is sized to the reactor it drops into. From that starting point, every feature is cut to the process. The number of pockets, their diameter and recess depth, the disc thickness, and the coating are each matched to the wafer and the reactor, and details like lift pinholes and edge chamfers are added so the susceptor seats and unloads cleanly. A non-standard layout simply follows the tool it serves. In the metal organic chemical vapor deposition process that grows gallium nitride films for LEDs and power devices, the susceptor carries the wafers through the reactor while precursor gases flow across them at more than 1,000 degrees. Because the disc holds every pocket to the same temperature, the crystal layer grows to the same thickness and composition on each wafer, so a whole batch comes out matched rather than scattered. The high purity keeps metal atoms out of the film, the corrosion resistance lets it ride through the ammonia and hydrogen unharmed, and the smooth pockets keep the gas flow even over each wafer. Lifted out at the end of the run, the wafers carry an even, mirror-bright film from center to edge, and the susceptor goes back in for the next batch unchanged by the heat and the gas it just endured. The uniformity it enforced shows up directly as chips that all perform alike. Meticulously, one machined disc turns raw heat and reactive gas into a flawless crystal layer, the quiet stage on which every wafer is grown.